Let's work on a problem that's a lot like one of the homework problems, but I'm going to do it in a more complicated way, and then you'll feel relieved when you do the more simple homework problem, right? So I found some interesting data on the utilization or the demand for various subways across the world. I found Chicago, Ann Arbor, actually transit rather than subway, Toronto, New York City, Paris, London. So here's New York City. Here's time from 0 to 24 hours, and this is the relative utilization. So as a percent of the maximum demand. So this is a kind of interesting function, right? How would you model this function if you wanted to use traditional calculus kind of formulas on it? Well, I used an idea called Fourier series, and I added like a sine wave and a cosine wave, and then a sine wave that goes twice as fast, and a cosine wave that goes twice as fast, and then 3 times as fast. And so the real data is in blue here, and my approximation is in orange. Would you say that's a reasonably good approximation? I would hope so. And for pedagogical purposes, I also changed the units from hours, 0 to 24, to fractions of a day, from 0 to 1. So let's take a look at what this orange function is written as a calculus expression. So here's our rate function in terms of people per day at any particular time of day. And I had to make some educated guesses translating from relative utilization to actual utilization. And I'm not saying this is the utilization of the entire subway system, but just like one line, like inbound to Manhattan on one particular line. So it looks reasonably complicated, I would say. Notice what we're doing here. We're doing an amplitude times cosine plus an amplitude times sine, so that's the once a day wave, and then an amplitude times cosine of 2t plus another amplitude times sine of 2t, so that's a twice a day wave that gives us a little more flexibility. It doesn't have to be a pure sine wave, and then a 3 times a day wave here. And let's say that the service rate capacity, the maximum number of people this train line can carry, is 680,000 people per day. So we want to do things like say, what's A of t? It's the number of people who have arrived to use basically the subway platform to wait to get on the train by time t. And we're going to say d of t is the number of people who have departed by time t. That is, they got there and they got on a subway. Maybe they had to wait, maybe they didn't. And if those are the same, then there's nobody waiting. But if a of t is larger than d of t, then more people have arrived than have left, so we have people standing around waiting. That would be a queue of people, right? So q of t would be the number of people in the queue, the waiting line at time t, which is a of t minus d of t. And we might want to say, what's the average length of the waiting line? And we might want to say, what's the average weight per person? So now we're going to turn to Desmos, and I've got some stuff defined here. Let's make it a little easier to see. So instead of saying 0 to 24, I'm just saying my wavelength is 1, like 1 day. And then my frequency multiplier is 2 pi over my wavelength. And I'm calling that W because a lot of times for frequency multipliers we use omega, and omega is a Greek letter that looks an awful lot like W. So that's what we're going to use here in Desmos. We just defined our capacity as 680,000 people per day. And then we're drawing a horizontal line at that capacity here. Here's our rate function. It's really long, right? It's all that stuff I had shown in Excel. So I basically just had to type that from scratch. That's why we try not to change software packages unless we don't need to. So the next thing I want to do is say, what is A of t? What is the number of people that have arrived by time t? To do that, I need to integrate the rate function, right? So I'm going to insert a new expression here. So I could say let's call it 1 of t equals integral from 0 to time t r of t dt. That's basically what I want to do. And I get this curve here. Does it make sense that that's always increasing as I go on in time and ask how many people have arrived by this time and this time and this time? That number always goes up because our rate function is never negative. We never have negative people arriving coming down the escalators to the subway platform. So that's one way to do it, but we also want to practice our by-hand calculus. So I'm going to get rid of that and say a of t is, now how can I do that integral from 0 to time capital T? That would be kind of the antiderivative at time t minus the antiderivative at time 0, right? That's how we do integrals. We take antiderivatives, plug in the upper limit, subtract what you get when you plug in the lower limit. So it seems I'm going to need the antiderivative of my rate function. So we could call that capital R, right? Let's insert a new expression here. So my antiderivative of the rate function would be the same amplitude times what's the antiderivative of this? It would be 0.637 t. And then what's the antiderivative of this thing? Well, I'll copy the constant multiplier. Antiderivative of cosine is sine. 1 times t times my frequency multiplier. But to do that antiderivative, I really should do a u substitution, right? And what happens every time we do a u substitution with a linear expression in the cosine here? We get du equals w times dt, and then we get a 1 over w. So I can throw this whole thing over w, and actually there'd be a 1 there as well. And I could just repeat that for every single term. So I don't want to take your time with that typing. I've actually got that hidden here. So you can see every time I have a multiplier on the t, like here I have a 2w, that becomes kind of a new amplitude multiplier, but actually dividing. So that's my overall antiderivative. Phew, that took a bit of typing. So now that I have that antiderivative, we can actually define the a of t function. And that's the antiderivative at time t minus the antiderivative at my start time. So we get the same curve that we had before, but now we've done the by-hand calculus. So that's good. Then the next part is what time does the queue start building up? At what time does the arrival rate exceed our capacity to serve people immediately? And that would be this time right here. So we could say the time the queue starts to build up, t sub q, is 0.5876. And there's actually a really neat way to have Desmos estimate that for you automatically using its regression function. So I do not expect you to do this, but it is a handy tip if you need to do fancy stuff in Desmos. We're actually asking it, what tq makes this true, that the rate at time tq is as close as possible to the capacity, and I'm telling it do stuff between time 0 and time 0.7 because I don't want to get this point, I want to get that point, so I'm restricting it to that to kind of this region. So it automatically estimates t sub q for me. So that's good. So then we put a point at that time and put a point at this time. And then the other question, another issue is, when is the queue done? You might guess it's here, but that's only when the arrival rate has dropped below our service capacity. We still have to work off the backlog. So this is not when the queue is done. That's just when we can start working off the backlog, basically. So the actual queuing is going to be done farther, finished sometime farther over here. We need to say, what is my departure curve? So let's add a new expression, d of t, and that's going to start here. Anytime before this, people arrive and depart immediately. They never have to wait because the subway train is full. So d of t is going to track a of t all the way along here. But once you hit this point, d of t can only increase linearly because people are departing at this capacity rate at a constant rate, but the arrivals happen faster. So I need a linear expression here that carries on from this point in a linear way at the maximum possible slope, which is the capacity of service, the arrivals per day. So I'm going to use point slope form. Let's remind ourselves of that. Y equals y naught plus m times t minus t0 or t naught. So I need some y value, and the d curve should be equal to the a curve at that time right there. So I've got it going through the right point, and then I need to give it the right slope. And what is the slope here? It's the maximum service capacity times t minus the, we'll have big T here. So it's kind of hard to see that there's actually two curves there. But there you can see the arrival curve is a little bit above the d of t curve. So we want to know kind of what's the average height here. That would tell us the average length of the queue, and also when does this finish. So time 0.7919, we'll call that t sub e, 0.7919. You might think, can we estimate that using regression? And you can try, but then that tries to adjust t sub q as well. It's a pain. All right, so this d of t formula is valid between there and there. So actually, we can put t sub q less than or equal to t less than or equal to t sub e. So then it will, oh, come on. No, let's undo that. So yeah, sometimes we fight with Desmos, but we really only want to pay attention to this curve, to this line from here to there and not farther out. All right, here we're defining our q of t function, and let's get rid of that. So how many people are in the queue at any particular time? Let's go see that. So that's from here to there. This stuff, we don't really care about it. That's not really real. So this is the length of the queue as time goes on throughout the day. Only the positive part. Ignore this part and ignore that part. So we could say, to compute the average queue, we could say take the area under that. So here we're having it take that area for us. This, in some sense, we should do by hand. But a of t is already pretty nasty. D of t is linear, but still kind of complicated. So I'm just having Desmos do that integral for us. Notice that a of t is already the antiderivative of something, and then I would have to take the antiderivative of that to do my integral here. This max thing is just saying if I do happen to go a little bit past over here, ignore the negative stuff I get, just treat it as 0. So that's the integral. Great. Maybe I have t sub e defined down here accidentally. Okay, there we go. So that integral is 614. It's not clear what that means though. That's people days of waiting. It would make more sense to talk about it just in terms of people or in terms of hours or something. So if I say, well, how many people did all this waiting? It would be however many people were there at the end or had arrived by the end, minus the number of people who had arrived at the start of the queuing. So that would be total days of waiting per person. And days of waiting doesn't make any sense, so we're going to multiply by 24 hours and 60 minutes. So we get an average of 6 minutes of waiting per person among the people who had to wait at all, not including the people who had 0 wait because they got there before the queue formed or after the queue formed. Phew, I think we're all done. Here's some credits for where I learned that regression trick. here's some information on where we got the maximum capacity, and that is how you can do an applied queuing analysis using traditional by hand calculus with a little bit of computational streamlining from Desmos. And in the next video, we'll go look at how you can do it in a spreadsheet.